Now, let's consider the alternating current circuit proper. Alternating current circuit. Number one. I told you we have three components. We have the resistor, inductor, and capacitor. Before I proceed, let me quickly show you the symbols of these three components. When you think of resistor, the next thing that comes to your mind will be the symbol for resistor. This symbol represents resistor. It could either be this or this. Either of the two represents resistor. Now, inductor is represented by this symbol. Take note of that. While capacitor is represented by this symbol. Note, the two vertical lines are of equal sizes. It's not as if one is longer than the other. When you draw something like this, it connotes something else, which is cell. Whereby this longer one will be the positive terminal and this shorter one will be the negative terminal. That is not the representation of capacitor. Please take note. The two vertical lines must be equal. So you have the symbols for resistor, inductor, capacitor. Now back to this. We are going to be picking them one by one. We'll pick pure resistive AC circuit first. That is, we are going to be dealing only with the resistor. The first thing to note is the circuit diagram. Circuit diagram. And how do we have it? It's just like this. This is a circuit diagram. This is your resistor. The next diagram we'll be having here will be the phasor diagram. It's from this diagram that we get the phase angle at the end of the day. The phasor diagram. We know we are dealing with pure resistive AC circuits. So the currents, that is IR, and the voltage, which is VR, are in phase. The currents, that is the currents and voltage, are in phase for pure resistive AC circuits. That is, the phase angle phi will be equal to 0 degree. There's another thing we call power factor. Power factor. And it is expressed as cos of the phase angle. So cos 0 in this manner will be equal to 1. Hence, the power factor of a pure resistive AC circuit is 1. Let's take note of that. The next diagram will be the vector diagram. Vector diagram. Look at, we have something like this. So the current is represented by this. Likewise, the voltage. So you can see the currents and the voltage are in phase with each other. We have it like this, just like this. So take note of that. Another thing we need to know is this. We recall from Ohm's law. Ohm's law. What does that state? Ohm's law states that the current flowing through a metallic conductor is proportional to the potential difference across its end, provided the temperature and other physical quantities are kept constant. Hence, mathematically, Ohm's law becomes V is equal to IR. And mind you, we are dealing with pure resistive AC circuit. So from here, we can say our resistance of the resistor being considered here will be equal to V all over what? I. In the same way, we recall from what I told you previously that Vrms is equal to V no sine 2 pi ft. Likewise, Irms, which is equal to I naught sine 2 pi ft. If this be is the case, we can easily say this our V here could be changed to Vrms, and this I automatically changes to what? Irms, which will be equal to V naught sine 2 pi ft all over I naught sine 2 pi ft as well. Something we cancel out. The sine 2 pi ft will cancel the one at the denominator. The one at the numerator cancels the one at the denominator. Then we'll be left with V naught all over I naught. Please, let's take note of this. It's very important. Then we can move to the second circuit. The second circuit, which is the pure capacitive AC circuit. So considering pure capacitive AC circuit, you know, current will flow through a circuit. Normally, this arrowhead is representing the current that will flow through the circuit. Here we have the capacitor and we have the alternator. That's that about that. For phasor diagram, we know that in a pure capacitive AC circuit, the current will lead the voltage. Current will lead the voltage by 90 degrees. This represents the current flow across the capacitor, and this line represents voltage across the capacitor. So you can see current is leading the voltage by 90 degrees. Please take note. So we can just conclude and say current leads voltage by 90 degrees. In which AC circuit? In pure capacitive AC circuit. Please take note of that. Hence, you know, I told you from phasor diagram we can get the phase angle. Hence, your phase angle phi is equal to 90 degrees. Take note of that. For vector diagram, we have it like this. Yeah, this represents the vector diagram. As you can see, this particular wave here represents the voltage, while the upper one here represents the current. This IC, VC. So it's proper to say current leads the voltage by 90 degrees. You already know that pi means 180. Pi rad is equal to 180 degrees. So pi all over 2 connotes 180 divided by 2, which will be 90. That is, current leads the voltage by 90. You know, semicircle like this, angle in this straight line is equal to 180 degrees. But when we now have a complete circle, that means half circle plus another half circle, which should give us 180 plus 180, which is 360. I believe you understand. 180 plus 180 will give us 360. But exact half of this 180 is 90. That's why we have 90 here, pi over 290. Here, this is complete semicircle, that is representing a straight line, which is pi 180. And this is 2 times of it. Look at 1, 2. So that's how we read this vector diagram. I believe you understand. That should be clear. Now, we're dealing with pure capacitive AC circuit. Since it is in terms of capacitance, XC substitute R in pure capacitive AC circuit. XC, what is XC? Capacitive reactance substitutes resistance. So in that regard, wherever we are to put resistance, it will change to what? Capacitive reactance. What am I saying? You know, from Ohm's law, we say V is equal to IR, R is equal to V over I. Instead of that R, we change it to what? XC will be equal to V over I. That is VRMS over IRMS, or peak voltage all over peak current. In the same way, I told you earlier when I was explaining reactance the other time, that XC, capacitive reactance, is equal to 1 all over 2 pi FC. Take note. You can combine all this together to later solve questions. Later on, we apply all this in solving questions. So, if the phase angle is 90 degrees, what then will the power factor be? The power factor will simply be what? Cos 90. Cos 90, which is 0. Take note of that. Let's move to the next one. Mind you, this is number 2. So far, we've considered the pure resistive, then the second, pure capacitive AC circuit. Now to the third circuit, which is pure inductive AC circuit. The circuit diagram is as shown on the board, where we have the inductor and the alternator in the circuit. Now, this diagram is expressed as this. Where we have the voltage across the inductor and currents across the inductor. So as shown on this, as shown in the diagram, the voltage leads while the current lag. That is, you can say current lag voltage by 90 degrees. So you can say current lags voltage by 90 degrees. Therefore, our phase angle will be equal to 90 degrees. Power factor, on the other hand, will be equal to cos 90, which is 0. That's about that. Now we move to the vector diagram. The vector diagram will be expressed as this. Yeah, this is the vector diagram. As shown in the diagram, we know that the current lags behind the voltage by 90 degrees, as expressed in the phasor diagram as well. So this is how the vector diagram is being expressed. So since we are dealing with pure inductive AC circuits, we know that XL, which is the inductive reactance, will substitute completely the what? Resistance. So instead of resistance, we substitute it with what? Inductive reactance. I didn't tell you the other time that reactance and impedance are also measured in ohm. So resistance, reactance, either capacitive or inductive, then impedance are all measured in ohms. Take note of that. They can ask you that. So our XL will be equal to V all over I, which would be VRMS all over IRMS, or peak voltage all over peak current, which could also be equal to 2 pi FL. Please take note of this. Let's move to the fourth one, which entails the combination of just two of the three components, RLC, resistor, inductor, capacitor. Here we are going to be combining RC, that will give us 1, then RL, 2, then LC. We just combine 2. We combine them in 2s. So we pick RC for the fourth one. Now, the fourth circuit, which is RC circuit, the circuit diagram will be like this. Like you already know, AC circuits are circuits arranged in series. So the components are arranged serially, like this in series. So we have the circuit like this. That's a circuit diagram. For the phasor diagram, we can have two possible triangles for the phasor diagram. We can have the voltage triangle as well as the impedance triangle. Let's pick the voltage triangle first. Voltage triangle, where we have stuff like this, like this, like this. And V. Yeah, this is the voltage across the resistor, voltage across the capacitor. Since we are dealing with resistor capacitor AC circuit, and this is the position of the phase angle phi, while this is the effective voltage in this case. That's for the voltage triangle. Then for impedance triangle is just going to take the same form as that of the voltage triangle. It's not different at all. We have our phase angle here as well. So this will change to R normally, while this will change to XC, and this will be our impedance, ZRC. So for the first one, we can easily deduce that the effective voltage will be equal to, we're having a right angle triangle here, then we should have Pythagoras theorem. We should put Pythagoras theorem in mind. Pythagoras theorem, which says that the square of the hypotenuse is equal to the sum of the square of the two other sides, which can be VR squared plus VC squared. Then this other one too will change to impedance ZRC be equal to R squared plus XC squared. Don't forget that the XC is equal to 1 all over 2 pi FC. Put that in mind. Put that in mind. Very, very what? Important. Now, we can also recall that our ZRC will be equal to VRMS over IRMS as well as V naught all over I naught. The same ZRC is equal to this. ZRC is also equal to R squared plus capacitive in reactance. Capacitive ZRC is equal to R squared plus capacitive reactance squared. Please put this in mind. Now, what should the phase angle be? What should the phase angle be in this regard? The phase angle could either be, from Socrates, tan inverse of VC all over VR, tan inverse of VC all over VR, or tan inverse of XC over R. Either of these two, that is, our phase angle could either be tan inverse of VC over VR, which is still equal to tan inverse of XC all over R. We can use either of the two depending on the parameters provided in any question. So that's about that for this circuit. We move to the fifth. That's about that for this circuit. Then we move to the fifth, which is RL circuit. So for RL circuit, the circuit diagram will be like this. Why? The phasor diagram we take the form of all this voltage triangle, impedance triangle. For the voltage triangle, so considering the voltage triangle, we can have it like this. So considering the voltage triangle, we can have it like this. This is the V, effective voltage. This is the V across the inductor. This is the V across the resistor. And these are phase angle. So from here, following Pythagoras theorem, our V, effective voltage here, will be equal to root of VR square plus VL square. Now the phase angle phi will be equal to, we can pick that from SOHCAHTOA, as I mentioned earlier, and toi is opposite over adjacent. Now the opposite here in this case is VL, while the adjacent in this case is VR, whereas the hypotenuse is V. So we can have it as tan inverse of VL all over VR in this case. Then for the impedance triangle, we can also have it to take the same form. So this will be our Z subscript RL. This is our XL, and this should be the R. So in this regard, it will be ZRL to be equal to R squared plus XL squared. And your phase angle will be equal to tan inverse of XL all over R. Please take note of this. It's very, very important. So from here, we can easily deduce that our ZRL will be equal to VRMS all over IRMS, or peak voltage all over peak current, or ZRL is equal to root of R squared plus XL squared. By the time we start taking questions, you will understand everything clearly. So we'll move to the second to the last, which is the sixth. That's the combination of L and C, inductor and capacitor, AC circuit. So here is the circuit diagram for LC circuit, inductor, capacitor, AC circuit. Now, the phasor diagram is very simple. It's just like this. Here we have the VL, and here we have the VC. You can either have it like this, or we have it as this in terms of voltage, while we can have XL, XC in terms of reactance. So now from here, you can see VC and VL are forming a straight line here. An angle in a straight line is 180. Hence, the phase angle in this regard will be 180 degree for LC circuit. Please take notes. In either cases, the phase angle is 180 degree. Now, for us to get the impedance which is ZLC, will be equal to root of XL minus XC all squared. Understand? If we consider this as a vertical axis, this is on the positive y-axis, while this is on the negative y-axis. So it is always VL, what is up minus what is down. XL minus XC. That was how we got this. That's how we arrived to this. So the square here, we cancel the square roots. Therefore, our ZLC will be equal to XL minus XC. Take note of this. In terms of V, we can now say our V is equal to root of VL minus VC all squared. So that when this square cancels the square root as well, our V will be equal to VL minus VC. So we choose the one to use depending on the questions and the parameters given. Take note of this. It's very, very important. Now, don't forget that your ZLC LC is equal to V RMS all over I RMS as well, which is still equal to peak voltage over peak current, which is still equal to XL minus XC. Please take note. And the phase angle is 180 for LCAC circuit. Now we move to the next. But before the next, ensure you hit the subscribe button. Is very important so that you can get all other videos that we'll be posting on this channel. Please, you need to follow up because I'll be doing a whole lot in this channel. This channel is aimed at simplifying the complex. We are here to make the complex simple. So hit the subscribe button. So the last circuit, which is the RLC circuit, of course, you know, this the components are arranged serially. We have the resistor, inductor, capacitors arranged in series. Then we have this alternator here. Of course, current will flow through. So that's that. Then we can move to phasor diagram. Phasor diagram. In terms of voltage, we can have it like this. Of course, I talked about the LC previously, to be expressed as this, where this will be our VL, and this is VC, of course. From here to here is VL, from here to here is VC. You know, this can be considered as vertical axis, where this will be the positive and this is negative, which will be that of the negative. We subtract that of the negative from the positive. Instead of us to have VL plus VC, this is tending towards the negative axis, so it's going to be VL minus VC. That's direct. So we have the R like this, resistor like this. Then, we have the VR like this, and this will be our V. Here we have a phase angle. So this is a representation of the voltage triangle. So that's that about that. So from here, our V will be said to be equal to root of VR squared plus VL minus VC all squared. Phase angle in this regard will be tan inverse of VL minus VC all over VR. Take note of that. Then in terms of impedance, we can have it as, all right, this will be XL, while this will be XC. We can have our R here. The phase angle phi will be somewhere around here, and this will be our impedance ZRLC, where our ZRLC will be equal to root of R squared plus XL minus XC all squared. Then the phase angle will also be tan inverse of XL minus XC all over R. Don't forget, our ZRLC is also equal to VRMS all over IRMS, which is equal to peak voltage all over peak currents. Take note of this. Now, let's move to another very important aspect of simple AC circuits, which is resonance circuit. What then is resonance circuit? Resonance circuit is a circuit through which maximum alternating current flow. A circuit through which maximum alternating current flow. That circuit, or the maximum current we are talking about, is I. And it's going to take place in the RLC circuit. And that I can be said to be equal to V all over ZRLC, which could also be rewritten as V all over root of R squared plus XL minus XC all squared. So this is an equation representing the maximum current that flows through resonance circuit. Hence, The current is maximum. The current of a resonance circuit is maximum. The current is maximum when the impedance is minimum. The current is maximum when the impedance is minimum. Please take note of that. Then we can also say resonance will occur. Resonance will occur. Resonance occurs when the inductive reactance is equal to the capacitive reactance. It occurs when the inductive reactance equals capacitive reactance. What am I saying? From here we can say 2 pi FL equals 1 all over 2 pi FC. So if we cross multiply, finally we're going to be having 4 pi square F square is equal to 1 all over LC, which can turn to F is equal to root of 1 all over 4 pi square LC. And that will be 1 all over 2 pi root LC. We can now say resonance frequency is equal to 1 all over 2 pi root of LC. So this is the formula that we can use to calculate resonance frequency. Please take note, this is very important. Now let's move to the very last aspect of this study, AC circuit, which is power in an AC circuit. Take note, power is only dissipated in resistor. Resistor only. You know, we dealt with RLC, resistor, inductor, capacitor. Power is only dissipated in resistor, meaning no power is dissipated in inductor or capacitor. So now, if that be the case, you should know that power is equal to IV. Then from Ohm's law, which states that the current flowing through a metallic conductor is directly proportional to the potential difference, provided the temperature and other physical quantities are kept constant. Mathematically, is V is equal to IR. So if I put this V, the IR is equal to V, I put IR here, I'll be having I square R. In the same way, if I make I the Sobel formula here, which will be V over R, put V over R instead of I, you'll be having V times V, that's V squared all over R. So we can use either of these three as the equations of power. So power dissipated in AC circuits can be given as P is equal to IV cos phi, or I square R cos phi, or V square over R cos phi. But most importantly, you must know that power is only dissipated in resistor, not in capacitor or inductor.